Imagine you're in a busy industrial plant. Machines hum, lights glow, and suddenly, there's a sharp smell. Plastic melts, wires overheat. The panel cover is hot to the touch. Inside, you find scorched wires and a burned bus bar. This could mean fire, equipment damage, or a total shutdown. That's why sizing breakers right isn't optional. It's essential for safety and peace of mind. Proper breaker sizing is a cornerstone of safe electrical work. If you choose a breaker that's too small, it trips too often and can't protect against overloads. Too large, and it won't trip fast enough in an emergency. The right size keeps everything working smoothly, stops nuisance shutdowns, and extends equipment life. Orientation matters too, especially with bus bars and three-phase panels. Bus bars distribute power from the main breaker to circuits. If the phases are connected out of order, motors run backward, equipment fails, or high currents flow in ways you didn't expect. The way you arrange the phases, L1, L2, L3, directly affects system operation and safety. Think of breaker sizing and bus bar orientation as two sides of the same coin. Both are about making sure the energy flows safely and predictably. If you skip these steps or make quick guesses, you risk real-world consequences that can cost time, money, and safety. By learning the right methods, you build trust with your team and protect the job site. Let's start with the basics of three-phase power and how it's different from single-phase. Three-phase power is the backbone of most industrial electrical systems. Unlike single-phase, which has one live wire and one neutral, three-phase uses three live wires. Each wire carries an alternating current waveform, but they're offset by 120 degrees. This means the current in each phase peaks at a different time, creating a smoother and more efficient flow of electricity. Imagine three waves in the ocean, each starting at a different point. When one is at its highest, the others are lower. This constant sharing of the load means motors run more efficiently, and power delivery is steadier. It's why industries prefer three-phase for big machines, pumps, and compressors. Three-phase systems are labeled as L1, L2, and L3, sometimes called A, B, C phases. When you connect loads across all three, the current is balanced out, and the wires don't have to work as hard. But to size breakers correctly, you need to know how much current flows through each phase. That's where the three-phase formula comes in. Understanding these basics gives you the foundation to make the right calculations and keep your panels safe from the start. To size a breaker correctly, you first need to know the load's current. For three-phase systems, the formula is I equals P divided by the square root of 3 times V times PF. Where I is current in amperes, P is power in watts, V is voltage between phases, line to line, in volts, and PF is power factor, as a decimal. The square root of 3, about 1.732, is a constant for three-phase systems. Let's break it down. Power is the total work your machines are doing. Voltage is what's measured between any two phases in the panel, like L1 to L2. The power factor accounts for how efficiently the load uses electricity. Motors, for example, might have a power factor of 0.8 to 0.95. Always use the correct voltage for your panel, like 400 volts or 480 volts. Don't forget the power factor. Ignoring it can give dangerously low current readings. Plug your values into the formula to get the current per phase, which is what your breaker must handle safely. Now let's walk through a real example so you can see the formula in action. Let's walk through sizing a breaker for a three-phase machine rated at 30 kilowatts. It's set up for 400 volts with a power factor of 0.9. Use the formula. Current equals power divided by root 3 times voltage times power factor. Plug in the numbers and you get about 48.1 amps per phase. Choose a breaker rated for at least this current, add a safety margin, and always round up to the next standard size. Now let's talk about why that safety margin really matters. Electrical loads aren't always steady. Machines start up, other gear gets plugged in, and sometimes the actual current spikes above what you calculated. That's why the National Electrical Code, or NEC, says you should add a safety margin, usually 125% for continuous loads, meaning anything running for 3 hours or more. So, using our example, the calculated current is 48.1 amps. Multiply that by 1.25 for the safety margin, and you get 60.1 amps. Your final breaker size should be at least 60 amps. You'll usually pick a standard breaker just above this value, typically a 63 amp or 70 amp breaker, depending on what's available and what the code says. This margin gives you a buffer against overloads, keeps your wires cooler, and helps your panel last longer. Never skip this step. If you size breakers without that margin, they might seem fine at first, but over time, they'll trip too often or fail to protect your system when you need it most. Balancing the load across all 3 phases is just as important as sizing the breaker. If one phase carries much more current than the others, you get what's called a phase imbalance. This causes overheating, stress on equipment, and can even trip breakers or blow fuses. To check for balance, measure the current on each phase with a clamp meter while the system is running. Ideally, the difference between the phases should be less than 10%. If you find one phase higher than the others, move some loads to even things out. Unbalanced phases waste energy and shorten the life of motors and breakers. Motors on an unbalanced system may overheat or vibrate, and electronic equipment can even malfunction. Keeping the load balanced not only protects equipment, but also improves efficiency and reduces operating costs. Always check phase balance after installation and during regular maintenance. It's a simple step that really pays off in reliability and safety. Bus bar orientation means the physical arrangement of the phase bars in the panel. The standard order is L1, L2, L3 from left to right. Connecting phases in the wrong sequence can reverse the rotation of motors, cause pumps to run backward, or even damage sensitive equipment. Check the phase sequence before energizing a new system. Some panels have clear markings, but always verify with a phase rotation meter. If you get the order wrong, fix it before connecting any loads. Correct bus bar orientation also helps with troubleshooting and future expansions. When every panel is wired the same way, you avoid confusion and costly mistakes. Remember, even experienced electricians can make errors if phases aren't clearly marked. A simple checklist and double-checking the phase order can prevent hours of repair time and expensive equipment failures. Safety first, always. Before you work on any panel, lock out and tag out the circuit. Verify with a meter that there's no voltage. Wear proper PPE insulated gloves, safety glasses, and arc-rated clothing. Keep your tools in good shape and use insulated handles. Follow these field steps every time. Double-check your calculations for breaker sizing, confirm the load's power factor and actual voltage. Add a 125% safety margin for continuous loads, verify phase balance using a clamp meter, check bus bar orientation and phase sequence with a rotation meter, and make sure all connections are tight and torqued to manufacturer specs. Label all phases and breakers clearly. Before energizing, walk through your checklist. Ask another qualified person to review your work. It's always safer with a second set of eyes. Good habits and careful verification keep you, your team, and your facility safe. Here's a practical checklist you can use every time you work on a 3-phase panel. First, identify the total load in watts or kilowatts and the actual system voltage. Next, confirm the power factor from the nameplate or manufacturer's info. Then, use the 3-phase formula to calculate current per phase. Add a 125% safety margin for continuous loads. Round up to the next standard breaker size. Check phase balance with a clamp meter. The difference should be less than 10% between phases. Verify bus bar orientation, L1, L2, L3, and phase sequence with a rotation meter. Inspect all connections for tightness and proper labeling. Complete a lockout and tagout, and wear all required PPE. Finally, have a second person review your calculations and setup. By following these steps, you'll ensure safe, reliable, and code-compliant installations every time. Take your time, double-check your work, and remember, safety and precision are always worth it.